In this unit, we are going to get more familiar with Paxos. And we will do this by going through a number of examples to understand how the Paxos consensus algorithm works, and also we are going to look if there is opportunities for optimization that we can do when we are running Paxos. So let us start. As a reminder, here is our algorithm. We call them Abortable Consensus. A proposer picks a unique sequence and sends a prepare message to all acceptors. The acceptor, upon receiving prepare n, promises not to accept any proposal less than n, and send the highest number proposal accepted so far. Then we get to when a proposal receives a majority of promises, it picks the highest value, if any, or it picks a free value and issues an accept, as we know that. An accept will go to the acceptors, and if the acceptor did not respond to a proposal greater than n, like in this case m greater than n, then it will acknowledge this. And once you get a majority of acknowledgements, then you can decide. Okay, and again, just make it clear is that the whole idea of the prepare phase is to ensure B, that V is the value of the highest proposal among all proposals less than n accepted by acceptors in S. So a prepare phase basically reserves the acceptors for not accepting any proposal less than n. And therefore, when somebody issues a proposal, it knows that it is the highest value among all proposals less than n. Okay, fine. You remember that? Now we go further and look what is happening in this algorithm. So remember that we have the following situation, that there are many sources where a proposal issued by a node will be aborted or not accepted. For example, contention, there are a number of proposals or number of nodes proposing multiple proposals at the same time. Messages may be lost and nodes may fail. For example, a node that proposes something dies, okay, in the middle. So that is clear. In general, proposers try to execute the abortable consensus instance that we just saw again and then again. So it might get run prepare 5 and then accept 5, then it doesn't get any acknowledgements, or it gets a negative acknowledgement, then it will go further and run prepare, say 15, with a higher ballot number. So eventually, if the system stabilizes, Paxos should terminate. But there is no guarantee to terminate in an asynchronous system. Remember, consensus is impossible in pure asynchronous systems because there are some execution that will never terminate. So let us see one of these. So what we are going to show now is a situation where multiple nodes contend in proposing at the same time. So there are multiple proposers at the same time trying to propose. And let us see an example of this. So here we assume we have two proposers, A and proposer B. Two of these want to propose. And they are contending, and you will see that there will always be a tie that we cannot break it. Here's an example. So A sends prepare messages and got acknowledgement from all acceptors. This is a set of acceptors. Okay, fine. And then after that, B sends a prepare message with a higher proposal number or ballot number, and of course he will get okay. So at this point, acceptors will not accept any proposal with a value less than 3. So now when A sends its accept message, so it has a certain value, it will fail because acceptors do not accept that. Now what can happen when it fails, either by timeout or by, say, negative acknowledgements? It can prepare a new proposal with a higher proposal number. So A now sends prepare with the value 4, and of course acceptor will accept this because he just promised to accept until the value 3. So they will accept this prepare message. And now, so the acceptor will accept the prepare message 4 from node A, and now accept message coming from B will fail. And you can see now we can go into this chain of events forever. So what we have now, we have proposals A and B forever race, and the only way to break these race conditions is to have an eventual leader election abstraction omega, which in the end stabilizes and only allows one proposer to become the leader, and that proposer will eventually, and the algorithm will eventually terminate. Eventually we have one proposer and then we get termination. Now let us look to another example to get familiar with Paxos, and just to point out that if we look to the set of acceptors, it is possible for different acceptors to accept different values. It will not be the chosen value, but it will accept different values. And it's also possible for a node to accept different values. So different nodes accept different values, and the same node accept different values. So let us see an example of this. So assume we have 4 proposers, A, B, C, and D, and we have 7 acceptors. So a majority of acceptors is 4. Remember that. Huh? So only when we get an acceptor, 4 acceptors accepting the same value, then the value is chosen. So here is the first situation. A proposes, and the first node accepts the value read proposed by A. After that, B proposes. Okay, so he sends a prepare message with a higher ballot number, and also goes to the second phase, accept phase, and sends a blue. So this is a situation where P2 now is accepting a blue, P1 is accepting a red. We can continue like this. We have a situation where C proposes with a higher ballot number or proposal number, and we have now P3 also accepting the value green. So at this point we have acceptor P1 accepting red, P2 accepting blue, and P3 accepting green. We can continue, and we say that okay, here we have D proposes. Okay, he gets an okay, that is fine. So he can go to the second phase, and here goes to the second phase, and because he is posing a value with a higher ballot number, in this case he get his value yellow accepted by a majority of acceptors. So this is yellow is a chosen value. So if we look to the different acceptors, we can see here that P1 accepts a red and then accepts a yellow, always with a higher ballot number, that's clear. B2 accepts a blue and then a yellow, and so on, and then only P4 that accepts only a yellow. Okay, so here we have a situation where acceptor can accept different values, and the next value to accept is a value with a higher proposal number. The most important property that we have is, and which is actually necessary for the correctness of the algorithm, is the property that we get when acceptors promise not to accept a value less than a value they just got. The necessary condition, if we look now to an acceptor, is the following: that reject any accept request with a proposal number n if the acceptor already answered a prepared message with m greater than n. This is the only important property to guarantee the so-called the invariant that we discussed before. I think the invariant was number P2C. So i.e. a prepare extract promise to reject lower accepts. This is the only one. The algorithm has to answer to reject such an accept. Okay, so let us have a look now. So here is a situation where what we are trying now to show is that we can do some optimization. Here's a situation where the algorithm only reject an accept request only if it has promised to accept a proposal with higher proposal number. Here you do a prepare. So the acceptor got a prepare with a proposal number 80. It's fine. The acceptors can also accept prepare with a proposal number less than 80. It's fine, but they will not accept any proposal in the accept phase that comes with a number less than 80. So now, when B sends an accept message with red, with proposal number 10, it will of course fail. The acceptors have already promised here not to accept anything less than 80. That's why this last stage will fail. So accept 10 will be rejected. One possible implementation is that why to answer prepare 10? So acceptors could either just ignore prepare 10 or send a negative acknowledge, say we will not going to accept you. That will save the effort of proposal B to avoid him sending extra message in the system. So no point of answering prepare N if anyway the accept of proposal number N will be rejected. Okay. So that is one observation. So until now we know what is our necessary condition, and we can also add an optimization which says reject prepare N if already answered a prepare M with a higher proposal number M than N, because we remember that a prepare extract promise to reject lower prepare. Just like now look to the following scenario. Here's a scenario. We start with, we have 7 nodes. We start with prepare with ballot number, proposal number 80. It has been accepted. Then a prepare with 90. It's fine. Now we only accept prepares with higher proposal numbers. Also is fine. And here B goes to the second phase and send an accept message, and the accept message comes with to accept the value red. And of course now we have established a majority, red will be chosen. And now if the node A comes with its accept message, of course it will fail here because this accept is lower than this promise. But because there's no promise at P5, P6 and P7, they will answer okay for this. But you can see very well that these accept responses is actually superfluous, and a proposal will never be accepted because a majority has already been established here. This majority had been established at this point. So clearly accept 80 can anyway not get a majority, as our property P2B guarantees every higher proposal issued would have the same value, and the value of a blue is not the same as the value of red. So these responses, okay, could as well be rejected. So here we are. So reject and accept with a ballot number N. That's what we're talking about. If you have already answered an accept for a ballot number higher than N. So in a sense, you can say that an accept extract a promise to reject lower accept. And we have also reject a prepare N if you have already answered accept M with a higher proposal number M. So an accept also extract a promise to reject lower prepare. So this is the now look to the following. There is one more thing that we have to think about when we are implementing Paxos consensus. So look to this possibility. Call it caveat in. So what do we have? Now let us look now to the possibility of one little bit extra optimization that we have to think of when we are implementing Paxos. Here's a situation where we send a prepare. We have 5 nodes. We get a majority of acts from the acceptors. We send now the accept message, which with the value read. This is a proposal to be decided, to be chosen. And we get here a majority. This is great. This is fine. No problem here. But what can happen is that the response, or the response to this prepare message for P4 and P5 can take a long time. So it will come later here, come here. Okay? And that is fine. It's just these messages, once you have already a value is accepted or chosen, you have just to ignore this. So ignore all the responses. That is one thing that you have to think about in the implementation of. So again, we have these 3 properties for optimization we can do. We have only one necessary action, reject, accept, and if answered, prepare M, and M is higher than N. And we have this A, B, and C. We can also add one more, ignore all messages to proposal that got a majority. So what is important now? What is the state of an acceptor? The acceptor, of course, remembers the highest proposal it has accepted. This is very important, needed when proposal asks for prepare, and also lower prepare will always be ignored. In any case, this is the highest proposal it has accepted. This is important, of course, to return the value to the learners. And then it has also to remember the highest prepare it has promised. It has to remember its promise. Promise to ignore a number of accept messages up to a certain number M. So it has promised to ignore accept M with a lower ballot number or proposal number. These are the 2 things it has to promise. So the highest proposal and the promise number. And to make an algorithm run in a fair recovery model, an acceptor has always to store these 2 informations in a stable storage. And once an acceptor starts again, it reinitializes the highest proposal and also highest prepared has promised. So these give us actually now an algorithm for Paxos for fail recovery model. Let us now go one further and say there are 2 more interesting optimization that we can do in an implementation. So first, observe that if we have a single proposer, we call it a leader, with no contention, a prepare phase takes 1 round trip. By the way, we call the prepare phase a read phase in some of the papers. An accept phase, which also we can call a write phase, takes 1 round trip. 2 round trips to execute. Now there are 2 interesting optimization that we can notice. Remember from property P2, if a value is chosen, every higher proposal chosen has the value V. Now a value is chosen if a majority of acceptor has this value. So one possible optimization, if a proposal runs the prepare phase and gets values from a majority of acceptors, and he got the same value, then this proposer actually knows that this is a decided value. So he can as well just forget about the accept phase or the write phase and just broadcast this is the value decided. So a proposer skips the accept phase if a majority of acceptor return the same value and can just broadcast to the learners that the value is decided and this is the right value. So this is a way to skip, say, the second phase. Here is another optimization which actually lead us to skip the prepare phase or the read phase. So often we need to run multiple consensus instances. And remember, in a prepare phase, the proposer needs not know a value. He just send the message prepare N or read N, whatever. And if we run many Paxos instances with leader base that we want actually to agree on a leader, and this is the one that's going to decide everything. So we can initialize the acceptors as if they have accepted a prepare one. We assume that the first proposal number comes from a designated leader thing called with ballot number 1. So we initialize the acceptor as if they have already accepted prepare 1 of the initial leader among all possible proposals. And initially, as long as the initial leader is running, so the initial leader runs only accept phase until suspected. Now, when he suspected, some other leader with a higher proposal number will take over. So subsequent leaders can run prepare for many instances with a higher proposal number in advance, okay? For many instances. In one message, can send one message with say prepare for instances number 5 to number 1000 with a higher, of course, with a higher ballot number. And so they need really to run then the accept phase or the write phase only. So we have a situation now where actually we are running the algorithm only quite often, only using one round trip. So performance, so in general, Paxos require 4 message delays, 2 round trips. In many cases, only accept phases run. So Paxos needs only 2 delays to terminate, and this is believed to be optimal. Okay, this is actually ends the explanation of the Paxos algorithm. What we are going to do after that is that we have an optional unit to look at the correctness of the algorithm based on the invariants that we discussed before. And the lecture after that, we are going to show a concrete Paxos implementation. Okay, thank you.